What's up, Sarah? You like my hood? I am the Senate.
Oh my god. That's so bad.
What was that?
What do you think it was? It was me being a hoodlum. Good morning.
Morning. I'm a victim of my own ideological position. I think PowerPoints are moronic, but I cannot remember everything I want to write in real time for this kind of handwritten lectures. I'm cheating. So instead of having PowerPoint, I have light text, which I hope you don't see, but you probably see, which I fill in as though I'm sliding a slide on the PowerPoint. Last week, we had a set of applications of complex analysis, which we need very often in practice, which are, very clean cut. You have to do an integral. There are always different ways to doing integrals, and we've chosen a set of integrals that can be done, one-dimensional integral, that can be done beautifully if you go into complex plane, and we evaluate them exactly using residue theorems. So that happens, sometimes we have this, but it's not a typical situation in research situation. In a research situation, almost always, we cannot analytically evaluate an integral. Almost always, there is part that we have to either estimate or do approximately or do numerically. And the complex integrations can be done numerically. People do this especially in chemistry. So the main idea about all these integrations where you go complex is that you're given some oscillatory series for some reason. Typically, if you're integrating over trigonometric functions, they tend to oscillate. Now, oscillating series are nasty because as you compute integral, you're getting something that goes up. So you get some contribution which you can estimate, but then it goes down, goes negative, or it drops. Then you estimate that. And now you have to add sum of terms, some positive, some negative, which can be, numerically every time you do this, you're losing accuracy. And in lots of situations that we apply this thing, we actually have to take very large positive terms, very large negative terms, and compute the difference. And this is hard. Sometimes you do it by brute force, but you're losing lots of accuracy in doing it. Now, complex analysis is amazing because you go into complex plane and it turns sines and cosines into exponentials. Cauchy's hyperbolic sines and cosines, which are sums and differences of exponentials. Now, why is that good? Exponential is very smooth, especially if it's decaying exponential. You always try to turn into decaying exponentials. So as you estimate these exponentials, you do very well because you're adding positive terms and they're falling off very fast exponentially. So that's the secret of going into complex plane when you're evaluating integrations. So if you're really lucky, you have a contour, you get a zero, or you get a pole, maybe you get a branch cut. But usually you're not so lucky, you don't have enough information about the function you're interested in the complex plane to be able to do this stuff. And then you led to the set of problems which we'll discuss today, which are very counterintuitive and surprising originally. And in 18th, 19th century, people were filling out blindly things that might or might work. So maybe they were just some kind of methods for computing sums, and these were just a bunch of tricks that you had if you were a good mathematician or applied mathematician. But in 20th century, they're totally central because it turns out the first step of trying to understand quantum mechanics from the classical point of view, from having understood the classical equations of quantum mechanics, or trying to understand ocean waves or many other phenomena which are wave in nature, that has few centuries of history. But these are theories called WKBs. So 3 people in the beginning of 20th century started them. And they turned out to give you extremely good approximation, just understanding classical physics. They're used all the time in all branches of science. And then you have to improve them. And these improvements, they're called perturbation theory. You might have seen Feynman diagrams. They're very pretty pictures in particle physics to watch. The example of such perturbation theories. And the amazing thing about these methods is that they're asymptotic, meaning for a while they look really good, and then they blow like a stick of dynamite on you. So we'll spend the week learning them, just because in their basic object in all of theoretical physics, you start with some very good approximation that you understand analytically. For example, harmonic oscillator, Keplerian motion, something that you can write down analytically. And then you start adding the so-called interacting terms or extra terms, which are supposed to be small in some sense. And that's how, many, many calculations are set up. And if you think about it, they all look fundamentally wrong, but after a while you get used to them. So this is asymptotic evaluations. These are these methods. So the idea is, and we'll do it on integral, we know how to do exponential solution of linear problem, but they call asymptotic expansions or expansions, but we'll focus on what we'll call asymptotic. I'll try to define it. So you replace an integral by a sum of terms, which you know how to do. So here is an example. It's called error function. So this is basically, it's drawn here. Basically just the half of a Gaussian. And the Gaussian, you think you know how to do, but now what you actually know how to do is Gaussian over infinite interval. That's a beautiful square root of 2 pi kind of result. But in practice, you have to estimate errors you make by not including entire interval. And that's why I look at error functions. And here is one example of thing that you don't have analytic answer for. That's why in mathematics, if you don't have an analytic answer for something, you give it a name. So it's called error function. It's integral from 0 to x. So error function just looks at a half of the Gaussian, of a Gaussian. So finite definite integral. And you say, well, for small x, what's the problem? Taylor series. You know what Taylor series of an exponential is? first term, second term, it's just factorials or turtles all the way down. There's a minus sign, so it alternates. And so on. Now, these are just now powers. I know how to integrate those. And the integration ranges from x to 0, so 0 doesn't contribute. First guy is just x. Second guy is x3 over 3 plus x5 over 5 times square. And I don't know what, yeah, everything is fine. Odd powers. No problem. So suppose that, x is 0.01 or 0.1. This is a nice series. X's to powers are small numbers. And you divide them by factorial. That grows like a bomb. So that series converges like ton of rocks. But suppose now, and that series, it's exponentials, it's always correct. Now suppose I want to compute this not for x equals 0.1, but I want to compute it for x equals 10, 100. I want to understand what's happening on the tail of the Gaussian. What error am I making by not taking care of that? You look at this series, it's a horrible series. Yeah. There's no way you're going to compute it because, well, mathematically, eventually, n over factorial. N factorial is larger than any finite x to the power n. You might need 100 or 1,000 terms before it starts converging. So that's why people go to what's called asymptotic series. They try to develop series in which you use information about the tail of the series. I have a colleague who said the following thing. Mathematical physics is three things. One, Gaussians. Two, integration by part. And three, I forgot, and every time I ask him, he cannot remember either what the third thing. But in this lecture, we're using two of those things. We're using Gaussians, and we're using integration by part. So what's integration by part? Let's take product of two functions. Take its derivative. Then when I act on the first term, I get derivative of the first term. So let's subtract that guy. I act on the second term. Now what we do is we take an integral on both sides. The first term derivative is anti-integral. So this first term is just the function inside a value at b minus function value at a. The second integral, I might know, I might not know how to do, but it has to be done. And this integral here, I might know or might know how to do, or the whole point is replacing that integral by something I know how to do, and integration from the beginning to the end of the integral. So that's integration of parts trick. You can move derivatives around when you have products of functions in the integral, as long as the full derivative, that's always doable because that's anti-integration. but if you gain some wisdom in doing it. So to evaluate something where x is large, we will use this trick. Again, we look at the error function. Now, we want to evaluate this area, but one thing we can do is we can take the Gaussian off to infinity and subtract the little part from it. So let's do that. And now error function is normalized in such a way. That's why it has a 2 over square root of pi in front. That you go to infinity, it's 1. So this is a small thing. And indeed, what we are doing, we are integrating here from here to infinity. So that should be small because exponential Gaussian falls off very fast. So this integral the tail of a Gaussian. I now use the integration by parts. So what I do is I decide that there is a function t minus 1 to t, and there is a function g of t, which is just the exponent Gaussian term. And now, if I just change the integration to t squared, then I will pick up, just in changing the integration from t to this being the variable, I'll pick up minus from the derivative 2 over t. So then if I call this guy my function g, and this guy is a minus here, the other function, then by rule of integration by parts, I can write this. So this is my f, and this is my derivative of g. I can write it as a product evaluated at two ends. So this is go to infinity exponentially 0 minus evaluated x. That's the term here. So this is this part of integration by part trick. And then I have to subtract this guy, which now is 2t squared dt. So now I've gotten one term, which for large x is small, because this is a small number, exponential, and it's even divided by the x. But now I have, an extra term to work in. Now I'll look at this term, this thing here. Well, it looks very much like the previous one, except the definition of f has changed because it's, now the f, the new one, in a new wash cycle is minus 1 over 2t cubed. Because if I take derivative of this, I'll get something that's squared. So now I wash and repeat. From here, I'll get ends of the integration minus x squared 4x cubed plus. And now I have this leftover term, this one. There'll be a factor of 3 I have to take care of when I take a derivative. That's why the 3 is here. And now wash and repeat, wash and repeat. And we get the formula for error function for x, where x is much bigger than 1, which is a pretty formula, pretty expansion. It says there is a normalization factor from the error function. Everybody has a Gaussian. That's great because that makes it look very small. And then I've picked up various terms. I picked 1 over 2x minus, next term was 2 square x cubed. And if you work it out, you start getting the feeling for what the answer looks like. So something like combinatorial is showing up here. It's the odd powers, odd integers multiplied, divided by odd powers going in powers of 2x squared.
So actually, the tabular method for the integration by parts, I really like it. It's really convenient. Do you know about that?
What do you call it? Tabular method?
Tabular method. Basically, you just write like your f and then your g, and you take derivatives of them, and then you until the terms disappear, and then you combine the terms in such a way that you get all the terms. You multiply the, I think it's like f by derivative of g or something like that in the table, so that you get all the terms immediately without doing the integration again and again and again, because you're doing it implicitly. Okay, I can send a link in the chat. That might be better.
Okay, send a link in the chat and I'll link it because.
Where did we get the 1 over t squared? The minus 1, the g of t, sorry, the f of t.
Where will you get this one? Or the next version? This one?
Yeah.
The first one was just obvious thing. We change the integrand, so we went to new integration variable, let's say u equals e to the minus t squared. Then we got du equals a minus, take derivative of this. This is 2 times t e to the minus t squared, right? When you change the variable, you have to compensate for this 2 squared, minus 2 squared. So that's why you put 1 over minus 2t.
Mm-hmm. Yeah.
Just change your variable. Mm-hmm. Now, once you have changed the variables, you have 2 functions because, you have original function was just the Gaussian, but now a new guy shows up in a product, which is this function.
Yeah, that's fine.
So the second function just came from change of variables. Mm-hmm. And then you use one wash cycle of integration by parts. That got us to a new integral, which has a different weight. Mm-hmm. So it has this weight in here. Now to make it derivative of something, we write function, so this is derivative of that function. And then you just repeat. Once you get 2 iterations, you can do as many as you want. And the result is, you look at this series, and you look at it and you realize, the general term in that series is minus 1 to the n minus 1, so it oscillates. That's obvious. Then upstairs it has odd guys, odd integers. So odd integers, you take even integer and subtract odd number from it. Turns out that 3 is the right thing to put in here. 2 to the n x, 2 to the n minus 1. And what you see is upstairs you have something that goes combinatorially, meaning that at every step you multiply it by a something linear in n. And downstairs there's something that goes as a power in n. So we're approximating our function by a series of terms and we're adding them up. So individual terms form a sequence and their sum is called a series or partial sum. And then we already discussed it. I don't remember whether I said this particular thing, but you have various tests on convergence of series. One of the tests is called Lambert ratio test. So if you have a partial sequence Sn is A1 plus A2 plus plus An, then you can compare the next term in the sequence in your partial sum. You look at its absolute value divided by the previous one, and you look at what is the limit of this as n goes to infinity. In our particular case right here, the next term has all these integers plus one more. So when you take a ratio, everybody's going to cancel except the extra terms. So I have to look at 2n plus 1 minus 3. That's the last term here. Now this is 2 to the n plus 1 x 2 to the n plus 1. So that's the denominator. I have to divide this by the previous value. So it didn't have 2n plus 1, this particular term. So that goes away. This is 2n x 2n minus 1. If x is fixed, because remember we were integrating Gaussian tails, so x was supposed to be fixed and we were adding more and more terms in the series. So x is some number. There is always an integer that's larger than that number. And if I take limit to infinity, this limit is infinity. This is a very bad series. So you would say, well, let's throw it out. Then you look at it more carefully because you have nothing else to work with. And eventually decide, we can live with this if we are careful. So Poincaré did this in the end of 19th century. He did it because he was interested in celestial mechanics. And there the calculations are always, you say, the planet is moving almost on an ellipse because that's solution of sun and the planet problem. Were it not for the other guys, but they're small. So what we do is we say the solution is ellipse plus a small correction that comes from the other planets messing with the planet I care about. That's called secular expansion, and it's First example, asymptotic expansion. It looks beautiful in the beginning, and then you get worried. So he defined what we mean by asymptotic series. So Poincaré said, consider the remainder. So if you look at function you're trying to approximate by the series and subtract from it a partial sum of n terms which is supposed to approximate it, call this a remainder. And the partial sum, because you're looking at this at x equals large, it's natural to define partial sum in inverse powers of x squared. Go in powers that are inverse, so this gets to be a smaller number. And then he said, perform two tests. Take limit for n fixed. So my nth approximation, and see how good is it as x goes to infinity. Now, if it turns out that that goes to 0, the error you're making, the remainder vanishes. You're doing a good job. It means that, roughly speaking, the error you're making is x over n plus 1, and that's going away. However, if you look at the same remainder, you keep x fixed and take a limit n goes to infinity. If this explodes, you have asymptotic series. So it says that originally we started defining something where we're interested in x going large and finding a correction. So the tail of a Gaussian was a nice example. Our method of doing that was by finding a bunch of terms in a partial sum. So we used wash cycle of integration for parts. That's typically what you almost always do in this kind of generating this kind of series. And it's good for something that wasn't the original problem. It says that I make an nth approximation and test how good is this for very large x. It's good. But then I go and look at what I wanted actually to do. I wanted to compute the integral for fixed x, meaning beginning of the tail of the Gaussian, and improve our partial sum. And that's a disaster. We just showed an example of it in the asymptotic series here that has vanished. So, this is an example of asymptotic series not working. Successive terms went off to infinity, so if you make a partial sum of the terms, every next term is larger by n. That's bad news. But then our predecessors developed by power of thinking methods, and the one that we use very often, so I really want to teach you that one, is called, it has several names when you run into it. So if you think of it in the way we will think in a complex plane, then it's natural to call saddle point. But if you do it like you often do it on a real line, and that's a method of approximating integrals, and I'll write it in a complex form. If you have some kind of contour in complex plane, and you have two functions, some, let's say, polynomials, some nice holomorphic functions of GT, and then there's another function, ft, and your parameter shows up in exponential here. You will be interested in large values of this parameter, because that's typically what we do in asymptotic integrals. Why do we do this? Originally, it came in because, for example, in Boltzmann statistical mechanics, the integrals tend to have this form where z is 1 over kt, k times the temperature. So as the temperature goes low, this goes high, and you need to evaluate with some Boltzmann weight. Or in quantum mechanics, this tends to be, there's an I over h bar, and z is inverse Planck constant, and you want Planck constant to be small when you're doing macroscopic calculations. So these integrals show up of that form very often. So if ft is real, then use what we call Laplace method. Check and estimate. This is our integral, Cf of t. So the dominant contribution is at the maximum of this function. So e to the zf at t0. And then there is some prefactor that you also evaluate at that value. And then you start one of these approximation methods, asymptotic series, start improving this. So, this is an estimate of a dominant contribution if the function is real. If the function is complex, this is not going to work because, if ft is pure imaginary, then what's going to happen is, as I look at the integrand, there still will be some width around the maximum. Let's say maximum is t0. So around the maximum, what happens is that, the function doesn't change much at the top of the hill. So this integrand will look okay in the interval of that width. But then as we go out, it'll start oscillating. And its amplitude might be, controlled by the tails of exponential of my function. But it's a nasty thing. Now, intuition about how this integral will be evaluated is that this will average out, and the dominant contribution will be the prefactor function, whatever it is. And now we take imaginary part of phi and write it as imaginary times our parameter, and then purely real function f0 dt. Where phi of t is imaginary part of our function. So we're assuming the case that the thing is purely imaginary. Now, if we do that, then it's obvious that if we can change our contour in our complex integration in such a way that it goes along the imaginary line, then this is going to turn into the previous kind of nice integral where the phi will be here, and the previous stationary, and now it's called stationary phase method. So then we'll use our contour technology. We'll start with an integral real line, it's oscillatory. And then if you close a contour and either has poles or no poles, so we know what contour gives, then we'll turn it around in such a way that it goes in imaginary direction through the peak of this function. And then Laplace estimate for the real function will work. It says it's dominated by the large exponential. Why is it dominated? Because there is this c that's going off to infinity, is getting to be large. And then when this is getting to be large, then this gets more and more peaked, and this approximation gets better and better. You know, if I'm at the zero at the maximum function, then z multiplying maximum will always give me 1. But at the moment I move around the maximum, this gets much smaller. This is roughly, inversely proportional to the sphere z. So that's how it works if the function is purely imaginary. Now, there is no reason for the function to be purely imaginary. All the functions we've been studying are mixtures of real and imaginary parts. And this is the reason why, in general, we have to face a saddle. So in general, what happens is that the integrand, or at least the thing that we have written exponential form, can be written as e of function w. We can always do that. We can take holomorphic function and write it as exponential function, some other function. The general function exponent, and now we have absorbed this parameter z into definition of function, has two parts. Has a real part, an imaginary part. And if you're looking at the magnitude of the function, you can just take the logarithm of the function, and it's u that controls the magnitude. Now, this function has points where the derivative vanishes with respect to z. And if derivative vanishes and they're holomorphic functions, we know the derivative vanishes in all directions. But then comes a non-intuitive, surprising thing that was due unexpected consequence of Cauchy-Riemann relations. We proved that a function that's holomorphic, analytic, can not have a maximum in a complex domain, because if you take any contour in a complex domain, we could find out that there was an oscillation of that function on the contour. And the highest value of the function is always on the contour, on the edge. So if you make it bigger and bigger, we get more oscillations, but we never get the maximum. So the only thing that we can have in a complex plane is a situation where we have a zero derivative, but then as we go away from zero derivative, in some direction we go down, and other directions we go up. And to describe this in a neighborhood of the point at which the function has first derivative equals 0, we do a Taylor expansion, and in Taylor expansion, the function has a value. So this is, z0. This is our C plane down here, invisible. That's a horizontal plane in here, but the vertical direction is the function W, our modular plot, just the value of the function. And around this point, there is a direction in which it increases. There is direction in which it decreases. And how do we find it? The first derivative of function there is 0 by definition. So we have second derivative is 0. And that's, if you think of it as a two-dimensional matrix, because, complex numbers are two-dimensional matrices, that will have two eigenvalues and eigenvectors. And there'll be one eigenvalue in which this increases and the other eigenvalue which the second derivative decreases. So now the idea of saddle point technology for whenever you're trying to approximate integrals is that down here in the complex plane, you have your extremal point. You used to have your contour that was running around goes knows where, because, you started with some contour. Typically, it's running along the real, but that's your contour C. And now what you'll try to do is you'll try to deform this contour in such a way that it goes through the saddle point. So this is now legal, we just deform it. Why do you do that? Because you're trying to get into this nice situation that as you cross the extremal point, not much changes. It has a constant value, so you can approximate it by this first estimate of Laplace. So that's why you go there. But now the next thing you want to do is, depending on what the contour does, it might wiggle. And you want to avoid this wiggling. So second thing you want to do is you want to orient the contour, that you avoid wiggling on the contour itself, so it's a nice exponential. So that's the whole idea of steepest descent method. Use contour technology like we used to use now to aid you in computing an approximate series, which turns out is going to be asymptotic series. But as we will learn on Thursday, asymptotic series can be insanely good until they become insanely bad. So in practice, they're wonderful and valuable. Let's repeat what I just said. So we're in a situation where we are neither the function exponent. It's neither real nor imaginary. So we can't just integrate purely real t or purely imaginary t. But it's holomorphic. And because of Cauchy-Riemann, which gave us these two Laplace equations, the equation has not a minimum, not a maximum, but we have found a value of it in our parameterization on a contour. T is parameterizing contour. Ft equals 0. And true both for real part and imaginary part. So the dominant contribution is you take f, which is up an exponent, and you split it into real part. That controls the magnitude. And then there is imaginary part. That controls the wiggles. in the same picture we were looking before. Here, we're looking sideways, but now we look from the top down. So this is looking into the complex plane. When we look from the saddle, we'll be either looking down in the valley, and as we draw equal height lines, you'll be looking down, or you might be looking up. This is looking here up the hill. If I just have some contour going through, then what happens is, if I go across the hillside, somebody above me on the saddle, so this is this contour passing by, you'll have a highest point called T0. This is just on the ridge as I look up. You say, well, let's take that contour because then this is really big and that'll dominate everything. But there is a price to pay because the imaginary guy is oscillating. So even though this would look like a good approximation, you have lots of oscillations. This oscillates like a crazy. So this is not a good calculation. So what you do is you deform contour and make it, go a little bit further down toward the ridge. And this gets to be smaller, but this oscillates less. But now if you aim it in such a way that you go up the ridge, the lowest point of the ridge, and down the ridge again, you get into this nice situation that you don't get any oscillation when you're on the top because the imaginary part is not there. This contour is chosen that this imaginary part is not there. And you can curve the contour a little bit to extend the regime where this doesn't oscillate. And then you get the optimal, So while this oscillates fast for contour C0, it's constant. For contour CS, let's say. Meaning S for going through saddle. So that's the idea of stationary phase approximation. So to summarize, you want to remove oscillations. You have freedom of choosing the path, and there is a path where you can remove them totally, in which you just choose for this particular problem, the imaginary part is constant. Choose a contour and a complex plane where you can do that. But by Kosher-Riemann conditions, if one value of function is constant, the other one has to change. So the real part, which by Kosher-Riemann is orthogonal direction. Because remember, we had always a landscape where real and imaginary part were 90 degrees for holomorphic functions. So real part of the function has to go through steepest descent. So near the saddle point, the function will have its value at the saddle point, Ts. Its derivative will be 0 by definition, it's a saddle. So the next correction will be 1 over 2 c t minus value of the saddle square. So I'll have to compute the second derivative of the function there. But then the rest one can compute, and one does. But we will only keep the quadratic, the first non-leading term, in our approximations. So this is in neighborhood of saddle point. And we'll need to also evaluate the function g, the prefactor, at the saddle point. And that function doesn't have anything special happening at the saddle point. So it has the first term in a Taylor expansion. So we'll keep as much of that function as we need. So near yes, that's what the functions look like. And now what we'll do is we'll change the variables, the new guys. To tau that measure the parametric distance on a curve away from the saddle point, and we'll absorb the prefactor into this. And so our integral, I'm running to the end of appointed time, but I will give you these notes, handwritten notes are due to Roman Grigoriev, and I'll give them to you on the homepage. We'll get a saddle point approximation to the integral they want to compute, which, will be from minus to plus infinity. We are really just doing kind of tangent approximation close to the saddle point, evaluate the saddle point, and then there is only a quadratic part to evaluate. And we just have to make sure that you have done your contour in such a way that this term is smaller than 0, the local curvature of the function smaller than 0. Then, function evaluated there. And because we have rescaled t, then in the series we'll have a correction of z minus square root dt z square root of t. Now we know how to compute Gaussian integrals always. So this is a constant, that's just a number. This is a constant, it's evaluated. And this Gaussian integral we can always do. And it always gives us square root of 2 pi. And then this number here shows up as minus c. That's a beginning of asymptotic expansion in powers of minus 1/2 of this variable. We have a hill, top of the mountain. Where is the top of the mountain? It's a complex landscape. So I'm in an imaginary real z-plane. So I find this is actually not what I thought was top of mountain. It's a saddle. It looks like a top of mountain if I approach it one way, but it's bottom of the ridge if I approach it orthogonal to it. So approach it this way. And now on the real line, that mountain as I go here goes up and down. So to the naked eye, it looks like a Gaussian because it has a top and the quadratic term, the first term is Gaussian. So it looks like a Gaussian. The correct thing has corrections which are next term other than quadratic term in the expansion. And the Gaussian always has the same answer. It's the square root of pi divided by the width of the Gaussian. Now the width of the Gaussian happens to be second derivative matrix in that eigendirection. So that's the idea of all these methods. And the official class is finished.